Welcome, everybody. Welcome to today's talk for PDC on F#. My name is Luke Hoban. I'm the program manager on the F# team at Microsoft. And today we're going to do a talk focused on two major themes. The first theme is going to be the F# programming language itself. F#, as you may know, is a new .NET programming language that combines ideas from functional programming and object-oriented programming into the language. It was originally developed in Microsoft Research starting about 5 or 6 years ago, and has constantly been developed through that period of time. But with the upcoming release of Visual Studio 2010, we're integrating F# directly into the Visual Studio IDE and the product, so that people will have developers on the platform will have a sort of stable and supported version of the tool set that they can use to build components of .NET applications. Now, F# is a strongly statically typed language, like C# and VB. And it enables everything from sort of an explorative style of development, which we'll see in some of the beginning demos today, up to a sort of large-scale component development using object-oriented programming. F# is a general-purpose language. So it's a language that you could, in principle, use to solve just about any programming, to do any piece of your programming work. But its particular feature set, as we'll see throughout the demos today, is specifically targeted at applications which are working in areas where technical or algorithmic or explorative or parallel work is a major part of the application. The second theme today is, of course, going to be parallel and asynchronous programming. And in particular, we're going to look at what tools F# as a language brings to enabling parallel and asynchronous programming and concurrency in general to be easier and more approachable within the programming language. Now, obviously, parallel computing is a big space. And we know it's a very complex challenge today. We know it's only going to get more complex in the near future. And to meet that complexity, Microsoft is bringing a lot of tools in with the current generation of its tool set to try to address this problem and provide tools to make it easier for developers. So you've probably seen previous sessions at this conference on some of these technologies here. There have been sessions on, I believe, every single technology mentioned on this slide. And these technologies provide an incredibly useful bed of tools for any developer on the platform, and in particular, also for F# developers. So many of these technologies here are things you can leverage as an F# developer and use within your programs. Everything from the fundamental layer of the threading and thread pools, which F# we'll see uses in a number of places. Some of the managed libraries that sit on top of that. We'll see examples of F# working with the task parallel library and touching on plink. And F# is well aligned. The functional programming style of F# works nicely with things like Rx and is well aligned with the direction that Axum is going in. And then obviously all the tooling support that's new in VS 2010 can be used along with F# to provide a nice tooling experience for debugging and profiling your parallel applications. But today we're really just going to focus on the F# piece of this puzzle. And in particular, we're going to focus on what F# uniquely brings to the parallel programming problems that we are facing. And so for the rest of the talk, I'm going to sort of pivot around a couple of major themes for big concurrency challenges that we have, and talk to what tools F# brings to the table to address those individual challenges. So the first one is shared state. So how many of you guys were here for the previous session on Axum? Many folks? So a fair few folks. So you heard plenty in that talk, if you were there, about why shared state is problematic. But let me quickly review some of the things for the folks who weren't there. So shared state in particular, I'm going to be talking here about shared mutable state to begin with. And shared mutable state is when I've got multiple components of my application which are using the same piece of memory, and at least one of them is writing to that memory. When I have this situation, it means that the different components of my application can have an impact on one another through this very indirect means. One can write to a memory location, and then later on at some point, another one can read from that memory location. And it means that these components can impact the behavior of one another in some very unusual ways, and some very unexpected ways, potentially. And the behavior of an independent component is not isolated from the entire behavior of the system and all of the shared state that they share. This can obviously make it difficult to test a component, because to get it into a state where you want to test it, you may need to have all the other components behaving in a certain way as well. It can make it very difficult to maintain software, because the interconnections between components are not explicit in the code itself. But worst, it makes it very, very difficult to parallelize the code. As soon as you have two components which you want to run in parallel, and they're both using the same shared mutable state, you almost immediately run into the need for locking. And locking is one of the truly difficult things to introduce into a piece of software and get absolutely correct in the implementation. So locking is difficult because we have to be able to identify what pieces of our code need to be locked. And this depends on exactly what's being shared and which different components of the system are sharing it. Now, if we add a new component or if we change the behavior of a component slightly, it may mean that new things are being shared between the parallel pieces that are running in parallel. Or if an existing component is suddenly used as part of some other larger parallel application, silent invariance that it had may be suddenly broken. And all consumers need to participate in this, but it's not manifest in the code. So the solution that F# espouses to this problem of shared mutable state is to really thoroughly, at the core of the language, enable, encourage, and make really easy the use of immutable programming. And immutable programming means that we just don't have shared mutable state, at least to a large extent. And we try to avoid it as often as possible. And so let's take a look in Visual Studio 2010 at what this looks like. So here I am inside the VS 2010 environment. And I'm actually going to start with some very simple demos here to start introducing you to some of the F# language. I'm expecting that some folks have seen a lot of F# before, and some folks have seen very little. So I'm going to start from the beginning and start with the basics, but I'm going to go fairly quickly through the material to try to touch on a lot of the parallel and async features in particular. So here we have VS 2010. As I mentioned, F# is built in, so we can go File, New Project. And we have a set of F# templates available in the beta 2. But to begin with, I'm just going to start in this very lightweight explorative mode that F# enables. And I'm just going to write some code here, like let x equals 1. I'm going to select that code, right-click, and click Send to Interactive. And you'll see that executed the code down here at the bottom and printed that the result was the value x of type int is equal to 1. And so you see that this F# interactive tool window is a new tool window as part of Visual Studio that enables us to interactively execute code and explore data and visualize that data on the fly. This is a very nice, simple way to work with code and work with data. So let's define some other values. We'll define the value greeting to be hello. And I'll select code and hit Alt-Enter, which automatically executes that code. And so you'll see me doing that throughout these interactive demos. And now let's define a simple function as well. Oops. And I'll say greeting for name is equal to greeting plus comma plus name. And so this defines a simple function. And there's a few things to notice about this. Let me first execute it and run it, just so you can see what that looks like. I can come down here and just type directly in the prompt if I want to. And so I say greetings PDC 2009, and that was printed out on the screen. So a few things going on in this simple code sample. The first is that the let keyword here is a fundamental keyword in F# for binding things to names. So those things can be either just values, like 1 or hello, and they can also be functions. Like in this case, the greeting for is a function that takes a single parameter name and returns this expression. You also notice some things like there's no curly braces or begin-end. Instead, white space is significant in F#, and so the fact that this is indented indicates that it's part of the body of this function. And finally, you'll notice that there's no types mentioned anywhere in this program yet. So the name parameter, for instance, doesn't have an explicit type provided at its binding site there. And in fact, F# has a very deep type inference system. And so things like the let here, which looks kind of like what you might see with var in C#, is one example. But this goes much deeper into parameters and other places in the language. That the type of the parameter name is going to be inferred from the fact that it's being appended to the end of another string. And so the fact that it's being used in that way indicates to the F# compiler that name must be a string. And this type inference doesn't mean that the language is dynamically typed. If I say greeting for 12, we'll see that I get an error telling me that this expression is expected to have type int, but was a string. So the last thing about this example is the concept we talked about when we came into the demo to begin with, and that is immutability. So when we bind these values, like 1, to the name x, you might expect that we could come along later and change that value. So for instance, you could change the value of greeting to be goodbye, and you might expect that this would change the behavior of the greeting for function to now print out goodbye, PDC 2009. In fact, the F# compiler tells me this is an error, and if I hover this, I can see this value is not immutable. And so by default, let bindings in F# are not mutable. And that means you cannot change the value of a let binding. And so you notice I've tried to avoid using the word variable to talk about these. And that's because it's really important to distinguish that these are just other names for that value. The value 1 now also has the name x, and the value hello also has the name greeting. So now you would ask, well, so how do I accomplish this? How do I write a function that can be parameterized over this string, this greeting as well? And this is something you're probably very used to already, but it goes very deep in what we do in functional programming languages typically. Instead of actually modifying the ambient environment in which a function is going to execute, we explicitly pass all the information it needs to be parameterized over to the function. And so we just provide it as an additional parameter. And this technique becomes very important and makes more concrete the dependencies between the components of our system. OK, so that was a very simple example. Let's look at another example of where immutability comes into play. So in this example, I've got a type named person, and it's an F# record type that simply has two properties, a name and a hometown. And I have an instance of that record named Bob, which I can construct using this record construction syntax. If I now come along and say bob.hometown, and I try to change that value to LA, you see again I get an error telling me that the hometown field is not mutable. And so it's not just let bindings, it's also fields of data structures. All throughout the language, we have this notion of immutability by default. And again, we could go and mark it as mutable and work around it like that. But what we'd encourage, what we really enable people to do is to write the code using a different technique. Instead of modifying an existing instance, we'll use copy and update to just take Bob and provide him a different hometown. So in this case, I'll say Bob with hometown is LA. So this is also another fundamental technique that F# enables to make it really easy to write immutable code. And that is that here, instead of modifying an existing instance, we just create a new one. We share as much as possible of the previous instance. If we'd had like 20 fields in this particular record, we could have stored all the remaining fields as the same strings, the same data. But we then create a new instance of the record type itself and point to the new string for the hometown. And so this idea of copy and update and sharing is very important for enabling this immutable programming to be as efficient as possible. Now, we've looked at how to bind data and values. But ultimately, control flow is probably the most important part of where immutability comes into play. So let's take a look at a few simple examples of what control flow looks like in F#. So this is an example. Some of you may have seen Luca Bolognese's session last year introducing F#. This is an example that he showed in that session. And I want to quickly go over this just in the context of immutability to show you some of the interesting concepts that come up when you look at different styles of writing this code. So the first thing to notice is that F# obviously does enable you to do mutable programming. It does enable you to write for loops. It does enable you to write imperative code. And there's times when you're going to need to do that to interoperate with .NET in a rich way. In this first example, we do mutable programming. And to do that, we allocate a mutable cell, the accumulator. And then we have a for loop, which goes across the values and adds on the squares of each of the numbers, ultimately returning the value that's been accumulated in that local mutable cell. One thing to notice here, for loops that you're probably all very, very used to. For loops are a fundamental thing that depends on having mutation in my programming language. Since a for loop doesn't return any value, all it can possibly do is modify the state that surrounds it in a way that later code is going to then pick up on and process in some other way. And so this style of programming really relies heavily on the ability to have mutable values and fields in our program. It's also manifestly sort of not parallelizable in this form. You could imagine I could go and take the parallel.for that's provided by the task parallel library and insert it here. But of course, that's going to make my code incorrect. I'm going to be, each of my different threads running on my parallel.for is going to modify the accumulator. And since they're modifying the same shared state, at the end of the iteration of this, I'm going to end up with some random value sitting in my accumulator. And so I would need to actually introduce locking on this value and only update it, or do an interlocked dot increment or something like this to write this code correctly. Now, the common technique in functional languages for replacing for loops and things and other control flow constructs of that sort is to turn them into recursion. And so in this case, we can turn that for loop we saw into some simple recursion. So here we have a sum of squares function. It matches an input numbers. If the input set of numbers is empty, then we just return 0, because the sum of no squares is 0. And if it's not empty, then it must look like some number followed by some remaining list of numbers, in which case I've decomposed the problem into this case, and I know that I can just return the square of the first number plus the sum of the squares of the remaining numbers. This is just a very simple example of recursion, but you see that some of the language features in F# help to make this much easier, the pattern matching, to decompose a problem down into smaller parts and then process those parts independently. Now, of course, we can move that. So of course, this example, this recursion example still is not fundamentally parallelizable. This example, since it's using recursion, I can't just grab them each iteration and put them all in parallel. Each one has to happen one after another. And so the more ideal way to write this is sort of to raise the level of abstraction above either for loops or recursion, and to write composable units of control flow that I can piece together to make my application. And so in this example, in this third example, which is the way that we would typically actually write this in F#, we take the set of numbers, we pipe it to the function that squares each number and returns a new sequence. And then we pipe that to the function which sums all the numbers in that sequence. And this fundamentally, this kind of approach, this compositional functional approach, relies thoroughly on everything being immutable. If my square function was silently behind the scenes going and mutating my collection as I processed it, this wouldn't work. And so the fact that F# enables me to write all of these functions and do all my behavior in an immutable way really helps to ensure that this style of programming, similar to what you've seen with plink, really is effective. And I mentioned plink, and I actually just said switch this earlier. Because we have plink, we can also enable this style of programming to just simply parallelize. We can just change it from seek to pseek, and suddenly we're using the parallel versions of these, and we're doing parallel looping over those collections. So when we write it in this last form, we've abstracted it to a high enough level where the parallelism is very easy to introduce. OK, so everything so far has been fairly sort of simple kind of toy examples. Let's start doing some more real kind of development with F#. And so the running example I'm going to use throughout much of the rest of the presentation today is going to use the Azure Blob Storage, which is storage up on the cloud in Azure. And it's going to use that blob storage. I've got some images placed up there. And I'm going to go and download those images and store them onto my disk. And I'm going to do this using a simple user interface. And so you see in F# we can do a few things. We can add references to .NET assemblies. F# is just a .NET language. We can add references just like we would in C# or VB. We can open .NET namespaces. And let me make this bigger so we can see what we're doing. And then we can execute just standard calls to .NET APIs. So this .NET API is the one that the Azure SDK provides for connecting to Azure Storage. And so we can connect to the storage. We can open up the photo gallery container that I have defined in my Azure Storage. and then we can create that if it doesn't exist. And now we can come and just write some simple code like container.listBlobs. We can execute that, and after a second, it comes back and it gives us a whole bunch of information about all the blobs that exist in my Azure storage. So we can use this to easily bring data now into the F# interactive. So now I've connected up to my Azure storage, and I can bring all that data into the F# interactive and play with it. And you can imagine how this kind of capability makes it very easy using all of the rich .NET APIs for accessing things like SQL and files on disk and web services and Azure, and then using presentation technologies like Windows Forms or DirectX or whatever we want to go and richly visualize the data that we're pulling into the F# interactive. But I want to quickly show what this looks like if we want to go and turn this into a more reusable component. So in C#, we would typically take a piece of code like this, and we would put it in a class, and we would provide a set of members to work with it. And I mentioned at the beginning that F# is a functional and object-oriented programming language. So let's see what the object-oriented programming looks like. So we'll call this the Azure Image Downloader, and we'll take a folder as a parameter. And I'll just put all of this code in the body of the function, in the initialization part of the function, of the type, sorry. And then I'll put this as folder. So now inside the type, I can expose a couple of properties, so a couple of members. So I can define a property named folder, and I can also define a method named downloadFile, which takes a file name. And this downloadFile method just takes container.getBlobReference for file name, .download text. So this is just using the Azure SDK. So ultimately, what we've done here is we've defined some simple F# object-oriented programming, which defines a class named Azure Image Downloader. The class has a single constructor, which takes a string called folder. In its constructor, it runs a bunch of code to connect to the Azure storage and initialize that connection. And then it exposes to users. It publishes a property, which has only a getter named folder, and a method called downloadFile. And we've been talking about immutability here. And people often associate OO programming with mutability, with having mutable state within your objects. But this right here is actually an example of using object-oriented programming in an entirely immutable way. There's no setters. All of my methods just return data. They don't actually mutate the state of the object. And so this particular example is one, and many others, are ones where F# really encourages and enables immutable object-oriented programming. OK, so that's a really quick tour of F# and some of the places where immutability gets plugged into the language. And that was actually only just touching on the surface of how deep immutability is in F#. So immutability is enabled in F# through both the language features that we've seen, plus a number of library features. We have immutable lists, sets, and dictionaries. And we have immutable tuples, which are now part of .NET 4.0. And then there's also a host of additional language features that make it really easy to program in an immutable way, like discriminated unions. And so immutability is really something that's at the core of F# and enables a lot more safety for doing programming with shared state. All right, so the second sort of big concurrency challenge I wanted to talk about is inversion of control. So we're very used to, when we write synchronous code, we're used to being able to just write one statement after the other. And sort of our code is very linear. And then as soon as we take that code and we want to make it asynchronous, we want to make it so that when it's doing some long-running piece of work, so some I/O operation, for instance, when it's doing that work, we don't want it to block the thread it's running on. And so we need to then split up that code, kind of take part of it and make it into a callback to the other part. We've got to add some logic for marshalling the state over to the callback. And then we've got to handle all of the weird cases that can happen with exceptions and cancellation related to the fact that this code is not linear. Now, asynchronous programming on .NET, there's quite a few APIs available for doing asynchronous programming, things like the begin-end methods that are part of the asynchronous programming model on .NET. But it's very, very difficult to use these. Using them truly correctly requires an enormous amount of investment in terms of checking a lot of different conditions. And it gets harder and harder as you try to combine more and more of these asynchronous computations together. Or even worse, if you try to put an asynchronous call inside a loop or inside some other sort of control flow. So let's take a look at some of the problems that are here, and then we'll look at some of the solutions that F# brings with its asynchronous workflows feature. OK, so we're going to take a look now at a simple C# application, WPF application, which is going to do this process of going up to the Azure storage and downloading some images and storing them onto my disk. And as it does that, it's going to use a file system watcher to watch when a file gets dropped on my disk and display it inside the user interface. So we've got a simple WPF UI here. The actual function itself, we have a downloader object, which is what we'll use to go and download the files from Azure. We have a file system watcher to look at the disk and to let us know when a new file is available to render in the UI. We have a bunch of setup logic here that I won't go into. And finally, we just call the download all method on our downloader. So let's go take a look at what this downloader looks like written in C#. So this is essentially the same code as we saw previously in the F# side, same object-oriented programming. And this is a class called Azure Image Downloader. It has a constructor which does that same initialization of the Azure storage. And then it defines two functions, download image, which goes to the blob in the storage and downloads a byte array of all of the data stored in it, computes a name to store that to locally, opens up a stream to write that data out to, and then writes those pixel bytes out onto the disk. And then because we want to download a whole bunch of these together, we're just going to write a download all function, which loops over all of the available blobs in my container and downloads each one of them. So this application, let's try to run it. Hit Control F5. Just a second to load up. If the network connection is slow, this can take a second to boot. Shouldn't take quite that long. There we go. OK, so we've got our simple application here. And we see that when we click the Download Images button, we're going to start downloading that data. Now, as soon as I do this, I run into a problem. My user interface has frozen here. So I try to move it around. I'm dragging right here. It doesn't react. I try to close it. I can't. The whole user interface is now frozen because I'm doing a bunch of really expensive work on my UI thread. And so this is fundamentally sort of problematic. UI is freezing because I have a lot of long-running work is a really big problem for any kind of user interface that we're designing. It becomes even more of a problem these days now that we're doing so much sort of long-running work. We're connecting to a lot of web services to pull data into our applications. We have enormous amounts of data available on disk that we're using to put into our applications. And when we do that, we just can't be doing it synchronously. We need to introduce asynchronous ways of writing this code. So let me just kill this program. Nope. Might have to come over here and kill it. That's the wrong one. Got too many of these things. There we go. OK, we'll kill this application. It would have eventually actually come back, but the network is a bit slow, so we won't wait for it to finish. So now let's try to make this asynchronous instead. So we know that the way that we can solve this reactivity problem of the UI is to make this program asynchronous. And so we just have a little bit of code here. Naively, we would think it should be pretty simple to make this asynchronous, to make the calls that are going to take a really long time yield control of the thread they're executing on and continue only when the data is available. So it turns out it's not really. Here we have an asynchronous implementation of this code that starts here and continues for a little ways. It required taking our two methods that we defined and breaking them up into 4 methods. It required adding a new type to marshal the data between the different parts of the callbacks. Even worse, because we were doing it in a for loop, because we were looping over a bunch of images, it actually requires us coordinating that looping. Because we have to invert the control, we need to do that using recursion. But that recursion could Stack Overflow if we took too many of these steps through this process. And so we actually need to also implement the behavior using looping and using this complex handshake between the looping and the recursion. What's worse, even with all of this code I wrote, there's a number of bugs and some design flaws in this particular implementation. It doesn't handle exceptions, doesn't handle cancellation, it doesn't clean up its resources correctly. And because of the way I wrote it, it actually relies on some shared mutable state here. And so it can't be easily parallelized. Each iteration depends on knowing what the values of these objects are. Now, all of these are problems we could solve. We could add another few pages of code here to solve the problem. But fundamentally, this is not going to be a tenable way to simply enable us to do asynchronous programming. So let's look at what this looks like in F# instead. So I'll come over here into an F# library. And this code now, all the previous F# code we saw was just part of a script, part of something that we executed in the interactive. We'll now go and do this in a F# library where we can actually expose our code as part of this C# application. So let's come over and grab some of the, let's grab the code that we wrote at the end of the last demo, this type. And now we're going to provide a different set of members, that same set of members that were provided on the C# class. And so let's grab those. And see, this is essentially the same code as that serial version of what we had in C#. We're just downloading the bytes, getting the name, opening up the stream to write to, and writing the bytes. And then in the download all, we're just looping over the blobs and downloading each image. So this code is very simple and very similar to what we had in the C# implementation. Let's try to make it asynchronous. So in F#, we have a concept called asynchronous workflows. And asynchronous workflows enables us to take regular F# code and embed it in an asynchronous block. When we have code inside an asynchronous block, it can be run potentially asynchronously. And that means that I can do a couple of additional things within that block of code. The first is I can put a let bang to indicate that this operation is going to yield control of the thread when it begins executing, and only continue running the rest of the code as a callback to that asynchronous operation. So I can do that. I can put async in front of this to call the asynchronous version of my download byte array. There's one other place in this code that is long running that could take a really long time, and that's writing out the file to my local disk. So let me do a do bang and call the async write method. The one additional difference is that I need to be explicit inside an async block about when I want to return my value. And so in this case, I'll return the file name at the end of the execution. Now, we also want our loop to be asynchronous, as we saw in the previous example. And so let's take this and put it in an async block. And let's actually change the name of our function to async, just to make it clear that this is now returning an asynchronous computation, not a synchronous computation. So we can use that here inside the async block. And we'll use let bang there as well. So we've introduced a number of points where at each one of these let bangs, the code is going to execute up until that point. Then it's going to yield control of the thread at the point where that asynchronous computation begins. And then it's going to continue running the rest of the code as a callback when the asynchronous computation completes. And this enables you to get that inversion of control, but without having to change the structure of your code. So you see that although we added a little bit of code here, we haven't actually changed the structure of the code at all. At the end of the day, we need to actually make this asynchronous computation do something. So let's run async.startImmediate to just start this thing running immediately on the thread where it began executing. So we can run this. Again, we'll take a second to start up the application as it connects to the storage. Oh, actually, I didn't connect this up to my app. Let me quickly come over here and change the using C# async to F# async. And build that. And run it again. So unfortunately, our network connection is a bit slow, so this is going to take a second again to load. But when it loads, we'll see that I have the same user interface. And the key thing here actually is that the F# code I've written, the object-oriented code I've written in F#, I'm able to expose to my C# code just like I would if I was writing it in C#. So just like I had the C# code before, I can do it in F# now. Let's run this. Give it a second. All right. OK, finally. So now that we've got this code running, we can click Download Images. And we see that after we click that, our user interface remains reactive. So now we're successfully calling these asynchronously. And we should, again, depending on whether our network is doing a good job, we should see the images populate in this dialog asynchronously. So I'll leave this running for a second to see if those images actually do start showing up. But maybe they won't. There we go. We got an image. OK. So the nice thing here is now by making some very simple changes to our code, we've really enabled the application to become responsive and to be able to update itself as it's running. One key thing about this actually is that I haven't introduced any parallelism into this application yet. Everything that's going on right now is actually still going on the UI thread. So the little amount of CPU work that we have to do here to coordinate these is all happening on that one UI thread where the application event was being, where the button click event was being handled. And this is pretty interesting because it means that we don't have to spin up a bunch of threads and manage the behavior between those. We can simply write our code in the same linear fashion, have it all execute on the UI thread, and just make sure that our asynchronous calls are being put in the right places. OK. So this sort of immediately brings us to the third of our interesting things. So one of the things you notice, our network is slow, right? It maybe is slower than I anticipated it would be, but it's definitely slow. And this is actually a problem, a real-world problem for a lot of software. So in practice, even though we often talk about parallelism in terms of leveraging our CPU to its fullest, in practice, many applications are actually I/O bound. And so for I/O bound applications, we really want to figure out how to best leverage the available I/O parallelism that's available with our devices. And so this is something that's important whenever we're doing things like we are here, where we're accessing web services or we're accessing the disk. And in both of those cases, those resources are actually very, have an abundant amount of parallelism available in them. If you think about the web, I can go and have many web requests go pending at once against many different web servers or even against the same web server. And those servers can feed back the responses in whatever order they feel like. They can process them in parallel using multiple load-balanced machines. Essentially, the internet and the web is fundamentally a very powerful parallel system. And so in our applications, we really want to be able to leverage that to its fullest, especially in an application like the one I've been showing that is very much I/O bound and very much network bound in this particular case. So we ultimately have a big opportunity to speed up our application performance and make it more better for users if we can leverage the I/O parallelism. So let's quickly look at what that looks like in this application here. So let's replace this download all with a function that's going to go and do this directly in parallel. Oops. So let's go and take our blobs. So we'll say container.listBlobs. And then we'll use our sort of compositional programming here. So we'll take seek.map, funBlob goes to. And now we'll create the asynchronous work to download that image. And just like we had the code in the previous example, I'm going to write that out again. So we'll say container.getBlob, blob.uri.toString. OK, so now we've got a bunch of asynchronous work that we can do. Now we just want to take all that asynchronous work, all these potentially asynchronous calls to the web service, and we're just going to put it in parallel. And so async provides an API for just parallelizing a whole bunch of pieces of async work, and then combining them into a single piece of async work that we can then process in whatever way we wish. Now last time we saw using async.startImmediate to execute that. We can also instead do async.start as task. And this starts it as a .NET 4.0 task object. And so this gives me back a task that I can use to check when this operation completes. So it's going to start it running, and while it's running, I can use the task to poll on whether it's completed or block on its value appearing. And this enables me to easily interoperate with all of the rest of the task-based programming stack that's available in .NET 4.0. And you'll see that there's actually a number of integration points where I can combine tasks into asynchronous programming and expose tasks out of asynchronous programming. So OK, we now have this simple example. Let's go ahead and try to run that one. And then let's hope that it's a little bit faster. Hopefully, because it's parallel, we'll get some of the images that take less time to load, and we'll get those into our program first. Of course, now it's taking a while to build. All right, wait for it to load. All right. So the fundamental, there we go. And we'll click the Download Images button. So we see it's still asynchronous, but now we see that the images that were very small and simple to download come back immediately into my user interface. And those images that were at the beginning, which were much bigger and took a longer time to download, will probably, again, take a long time to download. But at least they won't block the other work from happening. And in fact, even the total time to download all of the images is going to decrease quite dramatically when I run this. You also see that the utilization of my network is actually much more improved. I have overlapping network requests. So all of this data is being brought back in parallel. So I'm actually able to maximally leverage my network bandwidth to go and download these images. All right, so that was leveraging some simple network parallelism. There we go. So actually, before I go and move on, let me quickly talk to some of the sort of fundamentals of this async object that we've been using. So here we have just a very simple asynchronous computation that I'll use to show some of the behavior of asyncs. So in this example, we've got a simple program that's an async block that just prints that it's starting and then sleeps for 5 seconds and then prints that it's finishing. This is a simple example. The sleep here is not a thread sleep. This is just saying I'm going to pretend as though I'm doing some really long-running piece of I/O work. And we'll see what happens when we run this. We can do this in the F# interactive. And again, we can do start as task. So you see that it starts the computation running. And while it's running, I can actually execute other code. And then 5 seconds later, it prints that it's finishing. So this code is actually running concurrently with the interactions I have in my interactive window. Now, I can also take this code, and I can parameterize it. So I can create a whole bunch of asynchronous objects, each of which knows about what its identity is. And so in this case, I'll say I. And here I'll say I mod 5 times 1,000 to have them each wait for a different amount of time in the program. So now that I have a function for generating asynchronous objects, let's try to create a few of these. So we'll create 10. We'll take seek.map, and we'll create a program for each one of those. And then we'll do the async.parallel that we saw before, and then we'll start that as a task. So now we've combined 10 of these pieces of work together into one. And so let's run that. And we see that they start finishing at different periods of time, and we now have a bunch of different pieces of work going on concurrently. You may think that this is just like what we could do with threads. However, these things are very lightweight. If you remember correctly, if you remember what I said earlier, this thread.sleep is not putting to sleep the thread. It's just yielding control of the thread to anyone else who wants to do some CPU work. And so for instance, I can come here, and I can make it 10,000. I can run that. And although it'll take a while to print all these values out, it's actually not using up any more threads in my application. Oh, it didn't even take long enough for me to bring that up. So if I come in here, I see that FSI is still only using 20 threads, even though it's running 10,000 pieces of work concurrently in this application. So this is a fundamental thing. These async objects are very lightweight, very easy to compose, and very easy to use together in a system like this. OK. So that sort of sets us up for the fourth of our concurrency challenges. So as we look to leveraging parallelism more and more, we want to not just be able to handle multiple cores, a few cores on our machines. We want to be able to handle machines with many, many cores, hundreds of cores potentially, or situations where we want to scale up off of a single machine onto a multiple machine setup, where we have a distributed computation. And quite honestly, when we do have CPU-bound work, it tends to be the case that those folks doing really heavy CPU-bound work are already going and trying to find distributed computing environments, like they have access to a cheap cluster environment at their work, or they're using Azure to do load balancing of their server applications. So we want to write our programs with this idea of scaling up off of just a few cores onto sort of multiple machines or many, many cores. And fundamentally, what this requires, the fundamental difference between these multiple machine setups and our local setups is that we don't have any shared state, let alone mutable shared state. We don't have any shared memory that we can just all write to and talk to. And so we need to be able to write code in a way in which, as we talked about earlier with the mutable state, where the dependencies between components are more explicit, and where messages are passed directly from one component to another when there's a need to have some behavioral dependency. So this idea of agents and messaging is really the fundamental tool that's used when we go at scale for parallelism. There's many technologies for doing this. Many of you probably saw the talk earlier, as we talked about earlier. Axum is one of the technologies on our platform that uses sort of messaging and agents to enable this scaling up off of a single machine. And there's many other technologies like this. Many of you will be familiar with things like Erlang, which are built around the same idea of messaging and agents. So let's take a look at what messaging and agents look like in F# today. Now, today in F#, agents are sort of just a local concept. So we have agents that we can use locally. We don't have a story yet for expanding that smoothly up onto just sort of a distributed programming environment. And as you may have seen if you were at Nicholas's Axum talk, they're actually looking at taking some of the ideas from Axum, which do enable this, and integrating those into a future release of F#. And in fact, we're sort of looking, this is an area where we expect to continue F#'s evolution over its coming releases. But for now, let's just take a quick look at a demo of what it looks like to do agent-based programming locally in F#. So OK, we're back in our downloader here. And this downloader did some sort of, the code that we wrote inside the download all method was fairly ad hoc asynchronous programming. In the other places, we were composing together asynchronous blocks of code. But here we were sort of having to decide about the parallel structure, about whether to start it as a task or immediately. And agents enable us to encapsulate that behavior into a common pattern. So let's look at what an agent looks like here. So we can say let agent equals. And the type in the F# libraries, oops. All right, IntelliSense is not working. So the type in the F# libraries for defining agents is called mailbox processor. A mailbox processor is just a simple type that represents a agent that's going to be running on our code. And we can say .start. We can pass it a function which takes the inbox as a parameter. The inbox is where it'll receive its messages from other components of the system. And then there's sort of a pattern of how we write this. And I'll just write out the pattern and then talk about how this is overall structured. So the pattern is that we start inside our asynchronous agent here. We go into a loop, asynchronously process inside this loop, processing requests that come in to our mailbox, handling them, and doing some other asynchronous work along the way. So for instance, here I can say let bang message equal inbox.receive. As we've seen, because this is an asynchronous call, it's actually going to start the receive operation, and then it's going to yield the thread until work comes back, until some message is posted on its queue. And so it's not until someone posts some work to it that it'll actually come and start taking up CPU resources and memory resources again. We can then take that message, and in this particular case, we want to create a blob. So we say container.getBlobReference. And we'll pass it the message. And then we want to call our download message async. And since it's asynchronous, we can just say let bang file name equals download image async. OK, so there we've written a simple agent that encapsulates this behavior of being able to post messages to it, asking it to download images, and it'll go and do that work behind the scenes. We now don't have to worry about any of the coordinating the asynchronous work here. And instead, we can just say agent, we can say for blob in container, .list blobs. And inside here, we just say agent.post, and we post the, blob.uri.toString. So this is a simple way now of we can just coordinate between these two pieces of work. We don't have to know what's going on. We basically can just post work to it. We can post work from any thread in our system. And that work is just going to go onto the agent's queue, and it's going to process it when it gets around to it. This now should behave exactly the same as the previous one. In the interest of not wasting 5 minutes letting this thing load again, I won't run this particular example. But this now introduces that same asynchronous behavior, but does so using in-memory agents. Now, the one thing that we lose with this particular implementation is that it's no longer parallel. Everything is all the incoming requests are being processed serially. So we're doing one after another, waiting for incoming messages. If we want to introduce parallelism, we can actually use mailbox processors as a low-level construct to enable additional kinds of parallelism. So let's define a new parallel mailbox processor called parallel worker, which will take two parameters. It'll take the number, the degree of parallelism that we want for this particular parallel worker. And it'll take the function which executes the body of the parallel work. We can do mailbox processor.start. And again, we pass it the same kind of prototype. In this case, we're going to do something slightly different in the body, though. We're going to allocate a set of additional mailbox processors to do each of the individual pieces of work. So if we want to parallelize it 4 ways, we want to create 4 mailbox processors to do those individual pieces of work. So let's say let workers equals, and we'll say array.init n, and we'll initialize each one of these elements of the array to be mailbox processor.start, and we'll pass it f. So we're going to use that function that was passed into us as the function to run as the body of the mailbox processor. Now let's write our simple prototype for the loop. This time, though, we'll pass around an integer in the loop. So every time we go through the loop, we'll pass the next one of our workers to dispatch the work to. So we can say let rec loop I equals async. And inside the body of this, we do the same thing. We say let bang message equals inbox.receive. And then we want to actually dispatch that message to one of our parallel workers. So we say workers.add_i.post the message. And that sort of just asynchronously does the work. It doesn't block to call that. And so then when we're done with dispatching that piece of work, we just go back into our loop and wait for the next operation. Of course, we need to increment the integer. So we'll increment it and loop around n. And finally, we'll start our operation with loop 0. Now, we can easily use this now, instead of our mailbox processor.start, to just say parallel.worker 8, and pass it that function. So now we've allocated 8 of these workers to do the work. And one key thing, just like we saw with asyncs, that we can generate hundreds of thousands of these, similarly, these agents are very, very lightweight. Each one of them is just an asynchronous computation that's running. And so most of the time, it'll have yielded control, and it'll just be waiting for a message to come in. And so in this case, where we have 9 of these mailbox processors allocated, this is not allocating 9 new threads. We can have many, many of these agents all going at the same time. And so now I'll risk it and try to run this guy again, see how it works. And this should bring back the parallel behavior that we saw in the second example. So as I mentioned, these agents enable sort of a weighted program where our components, where our components are very isolated. They talk to each other only through explicitly messaging one another and don't have to rely on any shared state. As you saw in this particular example, we can share some state if we want to. But if we do want mutable local state, we can introduce that inside an agent, and it can be guarded by the fact that it's all inside a single agent running. So we click this, it should start it, and there we go. We're back to getting the parallel work being done, but this time using agents. OK, so thanks. OK, so we've seen sort of the 4 problems that we started talking about, and we've seen the 4 solutions to those problems. For shared state, F# provides a number of tools for programming in an immutable way, which avoids many of the problems inherent in parallelism and locking, and also in just general architectural of code that's more easily maintainable and testable. For inversion of control and I/O parallelism, and also reactivity, as we saw, F# introduces asynchronous workflows, which allow you to write your asynchronous code in very much the same way that you wrote synchronous code. And this is a feature that many of you may have seen in Luca Bolognese's talk, is being looked at as for a future version of the C# and VB languages as well. When we talk about scaling up and we look at where we're going to need to go with parallel programming, we know that message passing is going to be a very important part of that. And F# provides the tools to fundamentally write your code using message passing style, and to encapsulate your parallelism in agents using the mailbox processor type. So we didn't get much of a chance to talk about many of the other interesting things outside of parallel and async that F# brings. But I want to leave you with just like a few thoughts on that. So F# is ultimately a sort of simple and powerful language that you can use on .NET. That combines a lot of these ideas about functional programming into the .NET environment and the object-oriented programming you're probably very familiar with. In VS 2010, we're integrating that into VS, and so you can use all of what we saw here just in any .NET application. You can implement any .NET interface in F#, so you can take any small component of your system or large component and build that piece in F# where that makes sense. Fundamentally, F# enables a sort of simpler style of programming by raising the level of abstraction. And we saw that with immutability. We saw that with the compositional functional programming style. And we also saw that with the asynchronous workflows. And then lastly, obviously, parallelism and asynchrony are very important issues, both today and increasingly more so in the upcoming future. And F# has a number of tools to really help make this much easier. If you want to learn more about F#, I had to skip talking about many, many pieces of the language today, many of the things that make the functional programming in F# so nice. But there's plenty of information about those, plenty of links to case studies and other information about where F# is being used, what it's interesting for, what the best features are, up on fsharp.net. There's a number of books available on F# that you can go and grab. The book all the way on the left here, Programming F#, was just published by O'Reilly. And Chris Smith, the author of this book, is here at PDC. And so if you stop by the booth, you can talk to him about the book. He can let you know where you can get a copy. And for that, that's it for me. I welcome any questions you guys have, and thank you very much.